Well, hello ladies and gentlemen, it's your old pal Mr. Gibson here to talk to you about double angle identities, our last lesson in dealing with trigonometric identities. Yay! This really follows suit from the other three lessons as far as you have a couple of equations that you can apply to various situations, and it's up to you to decide which one to use and when and why. And that's basically the gist of it. So let's start off by looking at our little equations right here. We have our sine of 2 theta is equal to 2 sine theta cos theta, and the cosine of 2 theta is equal to a whole bunch of different things. So there's something interesting about this, and that's the idea that these are very different. And what do I mean very different? I mean different in the sense that there's more than one way to put in for cosine of 2 theta, which stems directly from the idea that cosine squared theta plus sine squared theta is equal to 1. If you input in for sine squared theta or cosine squared theta, you can get the other identity. So essentially in memorizing one, you've memorized all three. On the other side, this is obviously a little more straightforward, but at the same time, there's one thing to keep in mind, please, that when you see an angle like this, where it's 2 theta, this does not mean factor a 2. That 2 is stuck on theta and it's inside the sine function, so there's no way that in the future you're ever going to be able to factor that out in front of the sine, okay? So just don't. Alright, so let's use these in a couple of examples now. I'm going to work through a couple, then I'm going to give you the solutions to the other ones, just the actual answers, and you're going to be responsible for coming up with how we got those. But hopefully I do enough examples that that should be a piece of cake for you. So, first one here with A. We have 2 sine of pi over 12 cos pi over 12. That should scream at you that this is actually equal to the sine of 2 times theta. And theta in this case is pi over 12. And we end up with the sine of pi over 6. Now, you could use exactness to find out what the sine of pi over 6 is, but in this case, we wanted it as a single trigonometric function, so leave as is, okay? Let's look at part B. Well, again, if it's not 2 sine theta cos theta, then it has to be the cosine of 2 times theta. Again, that's theta. So pi divided by 8. And we end up with the cosine of pi over 4. Nice! C is a little trickier because we have a 3 and a 6 here, and if you look at our original functions, we have things that are 1 minus 2 sine squared theta. So what do? Factor out this 3. And what do you get? You get 1 subtract 2 sine squared theta. And then, of course, we can plug in that that is equal to the cosine of 2 theta. Sorry if my thetas look like zeros, that there is this big fancy theta. Okay? So, if you do D correctly, you should end up with the sine of 10x. E should end up with 3 sine of 4x. So please keep in mind that because of this 6, right, you're going to actually factor out a 3, but that doesn't affect these angles at all. Again, factoring doesn't affect anything to do with the angles inside the trigonometric function. F is a little trickier, so I'll take a look at this for you. We know that 2 sine theta cos theta deals with the idea of the sine of 2 theta is equal to 2 sine theta cos theta. Well, all we have to do is divide both sides by 2, and we end up with sine theta cos theta is just equal to the sine of 2 theta divided by 2. Again, and I can't stress this enough, when we take a look at this solution, those 2's don't cancel. The 2 is inside the trig function. I'm almost counting on the fact that somebody is going to make that error. So just don't do it. Okay? Well, we're in purple, let's stick with it. G, you should end up with 4 times the cos of 6 theta. Again, there's a factoring to be done beforehand. And with H, I'll do H for you because there's a bit of a tricky factoring involved. We have a 5 out front, but I know that our function actually deals with 2 sine theta cos theta. So let's factor out a 5 halves. Well, why did we do that? Because then we're left with 2 cosine of 10 theta sine of 10 theta. Well, that makes a whole lot more sense because now this just simplifies into 5 halves sine of 2 times 10 theta, which is equal to 5 halves the sine of 20 theta. So, major mistakes that people will make. They're going to try and factor out values that are on the angles. They're going to try and simplify expressions that just can't be simplified. And another one, which again I'll underline in red, they're going to forget to multiply by 2. So make sure that you do all of these things. If you aren't sure if you did it right, check it with your calculator. So in this case, again, much like everything in Pre-Calculus 12, you have the ability now to check your solution based on picking your favorite value for theta, your favorite value for x. It really doesn't matter what you pick so long as you're consistent in what you've input for. Either way, the expression that you started with should be exactly what you ended with. The value should be identical to the decimal. There should be no difference. Okay? So, that's our examples for part 1. I blew through those in a hurry. If you have any questions about the ones that I left blank, please feel free to ask or post on the forums or anything like that. Okay? So, we move along very quickly. We've seen questions similar to this where you're given the value for cos A and cos B and they tell you about these different quadrants. Again, this means it's quadrant 1 and this means it's quadrant 4. Yeah, I got it right this time around. And we're trying to find the exact value of the cosine of 2a. Well, we can use one of our identities, and because we were given the cosine of a, why don't we rewrite this as 2 cos squared a subtract 1. I'm just using the identity right from the top. And so what do we get? Well, we get 2 times, we know that cos a is 3/5. And this needs to be squared. Remember that cos squared a is exactly the same as cos of a, all that squared. It's just a different way of writing it out. And then we subtract 1 off that. And that's going to be equal to 18 over 25, subtract 1. I'm going to pull a math error yet again. And that's equal to negative 7 over 25. Done like dinner. Nice. So there's no dealing with the idea of trying to find the other side or anything like that because we didn't need to use the sign of A or B at this point. But if we take a look at B, and let's do this in pretty orange this time, let's see what we get. Well, we're looking for the cosecant of 2b, and we know we can rewrite this as 1 over the sine of 2b. Okay, well that's something that should tell us that we can input the double angle 2 sine b cos b. Notice that it's in the denominator because that's where the sine of 2b is. So don't try and pop things up into the numerator by accident, okay? And since we're running out of space, we'll do another one of these totally inappropriate arrows, and let's plug in some values. Well, we've got 2 times sine of b. Uh-oh, we don't have sine of b. So guess what? Dun, dun, dun. We have to go to our coordinate axis yet again. And let's take a look. So remember, this is quadrant 1, 2, 3, and 4. And we know that we're looking for sine b, and we're given cos b is 5 over 13. But we're told over here that B is in quadrant 4, which means we go 5 to the right. The hypotenuse is 13, which means all we have to do is find this side there. We know this is a right angle triangle, Pythagoras, and you'll end up with negative 12. Negative 12, remember, because it's in quadrant 4, we're going to have that negative sign to denote that we actually moved down in the coordinate plane. Think of this as a grid like we've been thinking about since grade 8. And in this case, now we can say that the sine of B is equal to, well, this is B right there, opposite over hypotenuse, so negative 12 over 13. Plug that bad boy in. Nice. Cosine of B is 5 over 13. Okay, which equals, I'm going to skip ahead to the final answer, but again, this 13 times 13 would be our common denominator, but it's the denominator in a fraction in the denominator, which means it pops to the numerator. Whole bunch of fractional math, but in the end you should get negative 169 over 120. So I've been asked a few times, well, do I have to put in a fraction or can I leave it as a decimal? This big fancy word here, exact, totally tells us that we have to leave it as a fraction. So even if the fraction doesn't look pretty, please, oh please, leave it as a fraction. Okay? We look at secant squared of theta equals all this junk over here. My gut instinct tells me right away, let's plug in for secant squared of x. And that's equal to 1 over the cosine squared of, well, it's theta. Beautiful. Well, what am I going to do with that? Well, if we take a look at one of our identities that we have, we know that the cosine of 2 theta is equal to 2 cosine squared theta minus 1, which means if we solve for the cosine squared theta, we will end up with 1 over the cosine of 2 theta plus 1 divided by 2. Again, fractional math, it's in the denominator. This little bad boy here is going to pop up to the numerator, and we're going to end up with 2 over, and just rearrange for fun, plus cosine of 2 theta. Beautiful. Left equals right, QED. I was asked a question, do I need to write left equals right, QED? Absolutely. This is a statement that you know you're finished your solution. So I'll just write this down. You admit to completion. In general, I say be proud of your solution. You worked hard for it. You know, show off the fact that, yeah, you're darn right, so I'm done. And be over with it, okay? Okay. Let's take a look at B. I'm basically going to work through B, then I'm going to let you try C and D, and then I'm going to work through E, let you work through F. We're done. This should be a pretty quick lesson at this point. So I'm going to use the pretty magenta to go nicely with the purple. Put that line right through the middle. Alright, so we got sine 2x divided by 2 sine squared x. Well, there's only one identity to plug in for sine of 2x. Remember that sine of 2x is equal to 2 sine x cos x. So plug that in. 2 sine x cos x, ooh, sloppy, over 2 sine squared of x. 2's cancel, 1 sine cancels, and what are we left with? Cosine of x over sine of x, which obviously, hopefully at this point, you realize is equal to cotangent of x, piece of cake, left equals right, QED. It's nice when you actually see how to get to the solution, because literally a proof could take you as little as a minute and as much as 10 to 15 minutes if you're really struggling with it. I'd say if you're struggling with stuff like this, get into your calculator, check your steps, make sure that you're doing the algebra correctly before you move on. Okay? Alright, so here's C and D. I'm going to give you a few minutes to work through it, and then we're going to explain some stuff. Okay, so get on it. Alright, ladies and gentlemen, hopefully we had a chance to work through that. Let's get to the solutions. Please remember that when we're practicing proper proving of trigonometric identities, that I always like to start with drawing the line right through the equal sign. It just helps us realize the difference between left and right. Now let's identify the obvious double angle identities that we have to deal with, and that's this cosine of 2x, which is equal to 1 minus 2 sine squared x. We also have this sine of 2x, which is equal to 2 sine x cos x. Nice. Let's plug all that stuff in. Look what we get. 1 subtract, in brackets, 1 minus 2 sine squared of x divided by 2 sine x cos x. Okay, so what? So let's take this negative sign and distribute it to both those terms. So we end up with 1 subtract 1 plus 2 sine squared x divided by 2 sine x cos x. Well, 1 subtract 1 is nothing. And so what do we end up with? 2 sine squared x over 2 sine x cos x. 2's cancel, one of the sines cancel. We get sine over cos, which is equal to, ta-da, tan of x. Left equals right. QED. Nice. So, one thing I will note is really important that you understand why this negative sign was actually distributed through. Always put your brackets around something when you're actually substituting into the equation that has a negative sign. Other than that, this was a fairly straightforward proof. Let's take a look at the second one. If we take a look at this equation, I'm going to start off by flat out expanding that binomial on the top and inputting for the sine of 2x. So let's take a look. I will end up with the sine squared of x plus 2 sine x cos x plus cos squared of x. And all that's divided by, we're going to leave this as the sine of 2x for a minute. You're going to see why, hopefully. Okay, well, we've got a whole bunch of terms here. Hopefully what you're seeing is this sine squared and this cos squared. If we rearrange things so that it says sine squared x plus cos squared x plus 2 sine x cos x, we can then use sine squared x plus cos squared x is equal to 1. What does that do for us? Now we get 1 plus 2 sine x cos x divided by the sine of 2x. Still haven't plugged in for sine of 2x yet, because hopefully it's becoming apparent that if we end up with a cosecant of 2x, we're going to need to see that it's sine of 2x at some point. So we've got two terms on the top in the numerator and one term at the bottom. Let's separate this into two fractions. 1 over sine of 2x plus 2 sine x cos x. Now, you'll notice that the numerator is 2 sine x cos x. The bottom we could leave as sine of 2x, or again realize that sine of 2x equals 2 sine x cos x, which means we can just input that right there. Reason being, hey, that equals 1. What does 1 over sine 2x equal? Well, that just equals the cosecant of 2x plus 1. Wait a second, left is equal to right. Rejoice, my friends. QED yet again. So, an idea I will say to this is just be careful that I know the gut instinct is let's put in all the identities we know, but in this case it was really nice to see that if you end up with a 1 over sine of 2x, you're going to end up with your cosecant of 2x, which is what you're looking for. So again, I looked at what I'm trying to get to and made sure that at the end of it, I ended up with that particular expression. Alright, so we're almost done, my friends. Let's move on to E. So I'm going to work through E, and I'm going to give you a chance on F, and then it's off to the homework or whatever else you're going to do. I think I want to go back to magenta. Magenta seems awesome. Let's divide our particular proof. Now, I'm going to let you sit here and think for a second. What the heck am I trying to do with this particular proof? Well, hopefully the first thing you think is, Well, I got this double angle here, I got that double angle there, and I end up with a secant of x. I should input for those particular identities. So let's do that. And what do we end up with? Well, cosecant is 1 over the sine of x times 2 sine x cos x, subtract 1 over cosine of x times. Now, this is where you have to think for a second. You've got a 1 over cos x here. You've got a couple of options for cosine of 2x. I'm saying let's go ahead and use the 2 cosine squared x minus 1. Why? Because we're going to get to cancel some stuff, and that's really the whole point of this, right? So let's take a look at if that did anything for us. This sign cancels with that sign, and we end up with 2 cosine of x. Subtract this particular item. Let's expand that through. We end up with 2 cosine squared x divided by cosine x, which is just 2 cos x. And then we have a subtract a negative 1 times a negative 1. So we get plus 1 over cos of x. Sweet. Look what happens. 2 cos x, subtract 2 cos x. Nice. What are we left with? Just 1 over cos x. Hey, guess what? That equals secant of x. Yay, left equals right. QED. We are just rolling through this today. All right, here's F. Take a couple minutes. Let's go. All right, folks, we're on the home stretch. Hopefully this worked out for you. If you had some issues with it, don't panic quite yet. We'll get through it in the end. So here's my division of left and right. So I've seen people that take completely different approaches to questions like this than I do. My advice to you is great. If it's working for you and you end up with the left equaling the right hand side, then you're good to go. If you don't do it exactly my way, don't panic, because we all have a different way of problem solving, okay? That being said, there's certain things that we should do regardless, and the first one is going to be, let's input for the cosine of 2x. So I'm going to pick something a little different that will hopefully make sense once I write it out. So let's do that. I'm going to use the identity that says cosine of 2x is equal to cosine squared of x, subtract the sine squared of x. And in the numerator, I'm going to input the sine of 2x is 2 sine x cos x, and I'm going to leave it as 1 for a second. Now, what were my motivations behind this for people that are wondering? Well, first and foremost, I take a look at the bottom here, okay, and I see this 2 sine x cos x. This makes me think of binomials that I've expanded to where I get that middle term, right? You know, with difference of squares, you eliminate the middle term. When it's not difference of squares, you end up with this middle 2 times the left and right parts of the binomial. The second thing is, if I take a look at the top now, I know that I can factor this out because it is difference of squares. At the top, cos squared subtract sine squared factored is equal to cos subtract sine x times cos plus sine x. Now, here's the trick. For that pesky little 1 there, I'm going to plug in the idea that cos squared of x plus sine squared of x is equal to 1. Now, why did I do that? Well, let's take a look. I'm going to go on a side note here. Let's call this my thought bubble. I'm going to end up with cos squared x plus 2 sine x cos x plus sine squared x. Well, like I said, this looks exactly like the product of cos of x plus sine of x squared, which means I can rewrite this now as cos x plus sine x squared. Okay? I'm going to put a big fancy purple star in this. This is a really tricky thing to understand the first time you look at it. It's not intuitive, the idea that you're actually going to plug in a particular equation for 1, but sometimes that's going to benefit you in the end. At this point, I would say that if that particular solution confuses you, take a look at the right hand side and see if you can manipulate it to start looking like the denominator that I just changed myself, okay? But if you do it my way, look at what happens. That cancels out and I end up with the cosine of x subtract sine x divided by the cosine of x plus sine x. Okay, well, what's the big deal? Well, check this out. I have cos subtract sine, cos plus sine. I know that tangent is equal to sine x over cosine x. So if I multiply the top and bottom by 1 over the cosine of x, which is totally legal, again, the same term divided by itself is just 1, so that's why we're allowed to do that. Look what happens. I'm going to get 1 over the cosine of x times cos x subtract sine x divided by 1 over the cosine of x cos x plus sine x. Okay, now these are going to expand through, and look what happens. We end up, the first term cancels, subtract sine over cos, which is just tangent of x, divided by first term cancels, plus sine x over cos x, which again is just tan x. Left equals right. I have no room over there, so I'll put it over here. QED yet again. So, big star. I want you to think, I need to factor something.